Yes, sir.
Thank you. So, very good afternoon. Possibly many of the participants or the speakers might be in sleepy mode, but it's okay. Sometimes we have to take a call on such occasions. Thank you very much, Gautam Buddha University, for giving us this opportunity to present the webinar based on that. I'm Dr. Sanjay, representing Subir Chaudhary Schools of Quality and Reliability, and my my presentation is part, in two parts, in fact. First is system effectiveness and reliability, meaning how they are related with, and another is based. Generally, people face how to specify reliability, how to measure reliability, something like that for a given system or so. So, this presentation based on this and the MTBF, which is commonly treated as a metric for reliability specification. So I'll begin my presentation and about my school. Briefly, I'll say that we are dealing with we are concerned with the research and education in the area of reliability and quality engineering, and basically we deal at the level of MTech at a research level, that is PhD. And you can get more details on our school. This is web test from where you can get. So, without wasting time, I come to the first part of my presentation: system effectiveness and reliability engineering. So, what is system effectiveness? The question arises: is it anywhere related to the RAMs? So, if you see from the historical point of view, you will see that system effectiveness had its beginning in the very early 60s. And you can say that after post World War II, there are two branches uh, came up in a very rigorous way. One was the operation research, because uh, this branch was related to the optimal resource utilization. Another was when the system is demanded to or the use, it was failing. So another area which dropped up was reliability engineering. So system effectiveness comes in early 60s, and major efforts was directed by two agencies. One was a effective a industry advisory committee, WCI. Another was ARING, Aeronautical Radio Incorporation. The first advisory committee presented 6 reports in 11 volumes. Possibly some of the reports might be available on internet, which involved in the totality of the requirement associated with the system's capability, which is a qualitative term, availability, supportability, dependability, as well as reliability. If you see, the reliability is one of the component of availability and supportability. And if you nowadays you will see the dependability term is taken up. So dependability, this reliability is also one of the component of dependability. And Dr. Rajesh has shown you one figure, performability engineering, where this reliability is again become a major component. Another component, definitely you will see the maintainability part, which overall gives you the availability part. So they published another contribution made by the ARIC, which was established in 1929 and providing a solution provided to several industries, right from aviation to the healthcare industry, transportation and communication industry, defense industry, government, several other government agencies, and they have given to place the importance of reliability, engineering in the overall picture and in the concept of system effectiveness, which encompassing reliability, maintainability, dependability, performability, operation readiness, physical education, and so on. So if you see how they have given the holistic view of system effectiveness. So system effectiveness is defined as a problem. It is a probabilistic measure, which has its three components. They are also measured in probabilistic way. So a system can successfully meet an operational demand on a general level. You can say this is the system effectiveness. And other part, if you see that this is system technical effectiveness (STE) or system operational effectiveness. another term. So as availability has been defined as a general term, and depending on the what are the downtime components you are incorporating, the availability definition changes like achieved availability or operational availability. Likewise, system effectiveness also can be defined depending on what you are taking into account. If you are taking the inherent capability, inherent properties of system like reliability, maintainability, and supportability, then that gives you the system technical effectiveness. But if you incorporate the utilization process of a system, which is driven by the operational scenario and the maintenance policy followed, then it gives you the system operational effectiveness. Now, coming to this, the design adequacy. A system is designed to meet certain design objectives. So probability of meeting those design in objectives is known as design adequacy. Recently, you have seen that the ISRO chief has claimed that 95% of the Chandrayaan-2 objectives have been fulfilled. So we can call that design adequacy. At the same time, mission reliability is given as once the system has started in certain mode, it will complete the mission in that mode. So this is again on a probabilistic basis. Third one is the operational readiness. Again, it is a probability that system will operate in the mode for which it was designed. Sorry. At any point of time, system can be made either found to be either in operable state or it can be put into the operation. So it can be in storage where it is presumed to be in operable state. The presumed word is has emphasis on where on that the system is in the operational state but is not being used. It is in idle state or so. The third term, which is availability, which has already been defined by Dr. Rajesh, I'll just give you an idea that availability is a component is depends on operating time, and operating time is depend on the reliability because once the system is operating, its completion of that mode depends on the reliability point that we call that it is related with the mission reliability. The other component of reliability is the downtime, which is a function of maintainability. How easily, how fast you can, the probability of restoring the system into functionable state. And this maintainability has several downtime associated with it. Active repair time, if you see the repairability and maintainability, they have similar definition, except that in repairability, we only consider the active repair time. And active repair time depends on the serviceability, where how fast, with what ease we can restore the system. The other time, downtime components are logistic time, where we try to see, we are waiting for certain special parts or certain team member, so it becomes the logistic delay time. And administrative time basically related to the various decisions are to be taken, like which say which team is to be sent out or other. So this is just I explained that the total time has operating time. It is so why reliability engineering? Actually, all the contract documents nowadays you will find they are having certain reliability and maintainability clauses in their specification, and this requires the understanding of those terms and terminology with respect to the reliability so that they can be interpreted correctly. Second is complexity of the product. You will observe that day by day the complexity of the product is increasing, and the customer demand is increasing to embed more functionality, sometimes driven by the requirement and sometimes driven by just for the sake of having those facilities. So, for having a high complex system to be reliable, their components and their lower order should also be highly reliable. Another Another thing, many of the products you will find advertised by the reliability and maintainability characteristics, and that forces completer to know their RAM characteristic. They should also find out how to generate such kind of data to quantify those RAM characteristics. Besides, learn how to quantify them and how to interpret such ratings to advertise correctly to have an edge on their competitors. Another thing you will find that concept of caveat emptor. It, earlier, uh, this caveat emptor concept is not valid nowadays. The meaning of this was initially it was the customer or the consumer's responsibility to assess the risk of using that system. So this is not valid nowadays. A company is liable for its product, legally responsible for its products. So anything is happening, company can be sued for such failures or consequences of failure of that project. Likewise, recent standards are moving towards absolute liability. Even a designer, a manufacturer, a store, a distributor can be sued for any failure uh, that is highly risky or so. So it absolves the user. So in other words, even a person can be sued and has sued for causing any harm to a community or the system. You can recall the Bhopal tragedy and Nokia battery replacement case for the same. So in this context, how the reliability engineering is going to help you. So the reliability engineering that provides the theoretical and practical tools to quantify the capability. In fact, I used the term earlier capability. Even initial reliability definition, if you go back, is the capability of the system to perform its intended function. Now the question becomes how this capability can be quantified. So the common language was found out is the probability, because every engineer can understand the probability of success of their own system, whether it is electrical engineer or civil engineer or so. So it can be quantified in terms of the probability of chance, and which can be specified, allocated, designed in, that can also be predicted before the product is coming into picture. It can be monitored, it can be tested, it can be estimated. And again, I am using the predicted term. Here, the predicted, when the system has not been in physical sense, but here it is estimated and predicted for the system which is already is existing. It can also be demonstrated to the customer that yes, the reliability, it has a particular reliability label with their maintainability, availability, safety, and quality label. Parallel to this, there is maintainability engineering. If I just change reliability here, REE, ME, maintainability engineering, and read it like this, so you will find that maintainability has a parallel space. Like maintainability can be specified, it can be allocated, it can be designed, and it can be predicted, and so on. So if I change, just to say that reliability engineering, and there is a parallel branch of maintainability engineering. So, what the benefits of reliability engineering is going to give you? It is becoming a customer requirement. The customer definitely demands certain functionality, and that should be reliable. And if they are not working properly, the irritation is caused, annoyance will develop, and company reputation is going to be on a stake. A company reputation is depending on highly on reliable products. If the products are reliable, then definitely the customers are going to buy again and again the products quoted by those companies. So the company will get the repeat business. Besides, they are going to have a competitive advantages on their competitors. You know that warranty cost is very much affected by the number of failures. If the failures are high, definitely the company has to keep some warranty reserve fund. It has to open some kind of repair center at the local level, at the the next level, and that involves cost. So, if the failures are captured, definitely warranty cost can also be curtailed down. Customer satisfaction is definitely, if customer is not satisfied, it is an old saying that one dissatisfied customer takes away another 10 customer. So customer satisfaction for a company is a very big issue. If the customer satisfied, it is going to get repeat business and other advantages. So considering all these factors, failure consequences and the benefits of reliability, then there exists how to establish, how to see that these reliability goals are to be specified. In other words, I am concentrating on only the first uh, uh, letter of RAM, reliability. So this way I am switching over to my next part, reliability. In the system effectiveness, you have seen that the reliability is coming out, the maintainability is coming out, and availability is coming out. So I'm from India. So I'll say in the Ramayana there is Ram and there is Sita. So RAM already coming in the system effectiveness module, but S is missing, means Sita is missing. So it does not mean that reliability and maintainability, in fact, implicitly addressing the safety issues as well. You remember that all the failures are related with the safety, and all the failures, you cannot say they are safety related, but many of the safety related issue can be resolved once one go for proper reliability and maintainability study of their system. So coming to the reliability, the next part of my lecture, the reliability specification. Reliability. First, a brief look at reliability design. You find this kind of flowchart in various textbooks where the system reliability in design, or for any design process for that matter, is an iterative process where we specify the reliability goal in the reliability context, which are consistent with the performance and the cost criteria. And this should be related to the life cycle cost and what reliability is going to have an impact on system effectiveness. So once the reliability goals are specified, they are to be percolated to the other parts of the system. At the very preliminary stage, you will find that the system is becoming a series model in reliability. So those reliability allocation can be done. There are methods available, and as the design improves, or design will involve, one can go for the reliability block diagram analysis and the corresponding allocation. And once the allocation is done, the various reliability implement design methods are resorted to. And these methods can involve the proper selection of parts and material, identification of technologies, stress strength analysis, derating, use of redundancy. So these some of the design methods I have say indicated here. There could be many more reliability-based design methods. So once the design methods are implemented, design has been reaching up to a stage, one can go for in parallel failure analysis where the FMEA, FMECA, reliability code testing, if the prototyping stage has been reached, one can go for the reliability code testing, or to some of the time you are trying to find out what would be the possible failure mode in the application areas, and some of the time you are just finding from the from the dying itself what will be the possibilities of failure of the system. So these kind of analysis are done, and based on the testing of actual system, then one can assess whether the reliability goals are achieved. If they are achieved, then one can go for the look for the validation and verification of the safety margins through the tools like FT or so. And once they are also met out, then one can ready for production. Otherwise, this goes on to improve the system and so on. So the reliability Dr. Rajesh has given you one of the definition as the failure-free operation of the system, the simplest definition. However, if you see what are the components of reliability, it is a comprehensive definition. It is a conditional probability. This conditional word is missing in many of the definition. At a given confidence level, you will not find this word in normal definition which you find in the textbook. That the equipment will perform its intended functions satisfactorily or without failure for a specified length of time when used in the manner and for the purpose intended. Again, this underlined word will you will not get. That's why I'm saying that is a comprehensive definition. While operating under the specified application and operation environment with their associated stress level. So one is the simplest definition, another is the complex, comprehensive definition. In between this, it is the IC, International Electrotechnical Commission, which has also quoted several standard on reliability study or analysis. They have given a definition which already presented by Dr. Rajesh in his slides. And or otherwise you can find in several books. So How to develop good reliability specification? That is the question many of the time you will find once you do the reliability studies. Even the most vigorous reliability testing program will be of little use if the product being tested has a very poorly defined reliability requirement. Why it is happening? Sometimes you will find the reliability requirements will be developed by a group which are not at all conversant with the reliability concepts or reliability data analysis. And this results into a very vague and unrealistic requirements that would little the aid in the development of the product. Another is, while most organizations are concerned with the reliability of their products, many will not be able to develop a very good reliability specification. And that becomes a serious flaw that can result in unreliable products are reaching to the market. So many of the times, if you see what would be the possible reliability specification, find, generally you can get in the requirement document. A new product will have a reliability that is no worse than that of the previous model. This is one of the statements you can hear. Another statement could be the product will meet or exceed customer expectation. Now, if there is no quantitative information about the previous model, which is worse, which is good, how you one can determine? And if it is to exceed customer expectation, then what is the measure of customer expectation? Another question one has to pray. But this may be useful as a general guidelines, but they become codified in the requirement documentation for the project as the reliability specification, which is slightly wrong concept. So essential elements of reliability requirement generally have 4 to 5 components. One is it should be measurable, which can be translated in terms of the probability statements, the probability of success or so, with a desired confidence level. At what confidence you will say that your product is so much reliable, how much reliance you are going to put into, with what confidence. And it also confidence level also captures the variability in the data once you are estimating the reliability, and also it addresses the sample size issue. We will see later what is meant by. Another is duration or time, or we call that mission time or operational use, and so on. The fourth component you will find operating environment, and the fifth component you will say that customer uses required. So operating environment can be put into either as a constant value or between the limits. Constant value means 25 degrees centigrade or so, using a limit plus minus 220 volts, something like that, or using time dependent user profile. These are the components. But at the basic level, at the essential level, there must be 3 components for specifying the reliability requirements. At a minimum, one should be the specified reliability, that is probability of success. Another is time over which it should be associated, and a desired confidence level. This definition has already given by. So many of the times when the system design is taking place, it must be adhered to what failure definitions you are following. Likewise, these definition you can always quote the standard, because many of the company wants that you follow some standards, so one can follow IEC standard or Willis standard. There is a requirement. So these failure definitions are related to the failure, and this is related to the process failure, equipment failure, unable to produce the confirmed product or so. My idea of given this, once you are recording the data, there is a failure categorization. You must know that what is failure, what types of failure you're governing with, and they must be recorded in a proper manner. So failure criteria, intermittent failure, where when the condition exists, the system, such kind of failures are only occurring. The extended types of failure require some kind of corrective action, and this extended type of failures could be catastrophic, which are the component complete, that is complete stoppage of the activity of the system, and they're sudden, they're appearing without any warning. Rather, degradation is you will find a gradual pattern where you can get the warning signal and the partial loss of loss of function of the system you will observe. So this is just like show you while data recording, you must address this kind of failures. You must know that what kind of failures you are recording and what is a failure occurring in the system. Another is again, this is a slide. This is again for the once you make a template for data recording. These are the things must be kept in mind that the failure causes are to also be to properly recorded, whether they are related with the design, whether they are related with the manufacturing, or whether related with the use with operational scenario. So these are going to be helpful to address the failure and the failure causes, and hence they improve the design. Just so these are the just explanation of this various types of failure. So another question which I try to say, if somebody wants to set the reliability goals for their system, there are possibly three methods. And one, you can formulate the problem as optimization problem, where you can calculate the reliability of several different configurations, or you can alternatively or combine with the same configuration with but different state of the art. So use a different art of the component with the same configuration or different configuration, you can create the reliability configuration, and the total cost can compute based on the usage of. So this is nothing but the life LCC cost estimation, and when you select the in this manner, you can plot it reliability of different configuration. Configuration one, what is the reliability and the corresponding cost. Configuration two, what is the corresponding cost of this system, and you can have a plot kind of thing where you can select the minimum cost criteria, and you'll find that configuration 4 has the minimum cost, and the reliability is you can set this reliability as your targeted reliability. Another method which can be components failure rate, and using the databases, like there are several databases are existing or the guidelines are existing for predicting the failure rate of your system based on the component failure rate models like 217 plus FIDES. You can have the database failure mode and distribution database. Right now it is 2016. You have the database like EPRD, NPRD, and this is another. This is Group of Industry Data Exchange Program. This is a consortium of different industry. We are sharing their information. You can find the details of this GIDP. One should be a member of this on their corresponding site. So one can predict using a multi-valued prediction. Many of the times you have the failure rate, the best failure rate, the lowest, high, most likely failure rate you can find in these databases. Based on this, you can evaluate what or predict the reliability of your system. So you are going to get three values. And if similarity based, if you're not finding the exact component in this or model in these databases or guidelines, you can subjectively modify such failure rate for the state of the art components for which failure rates are not available, and then you can select the target reliability somewhere within the predicted range. So at a very exceptional case, you can select the upper limit of predicted reliability. So these are the two methods one can follow to calculate reliability. But if these two methods are not working at all, then you can go for system reliability in excess of 85 degrees cent, 85%, or preferably in the excess of 90%. So it becomes a apportionment type of method where you are setting a target reliability at the system level, then allocating the reliability on the subsystem or component levels. So once you develop this reliability, now we see the three components which I said, the essential component, how you are going to specify. The first, you will see that usually you will find that the life or the reliability metric is specified in terms of either the mean time to failure or mean time between failure. For instance, this is 10,000 miles. 10,000 miles. Yes. 10,000 miles, or in terms of the failure rate, it is 0.001 failure per mile. So what uh, most of the time, how it is interpreted. And many of the engineers will find that they will say that possibly their interpretation will be that most of the system are surviving at 10,000 miles. Is it alive? And MTTF, if you are confusing with the MTTF and MTBF, the MTTF is generally used for the non-repairable system, and MTBF is used for the repairable system. This is the general difference you will find, and in most often, if you go for the modeling side, then the MTTF, if the exponential distribution can be modeled the time to failure, then you can say that this mean time to failure, you can say, or okay. So most statement of the MTBF are in terms of hours or kilometer or cycle. Easy to confuse with MTF. So once people are giving in terms of the days or years, then this specification is usually confuses that it is going to be lie, which is not the case. So, what the requirement writer thinking that random failure or exponential distribution is the model through which one can model the time to failure or time between failure of the product. So, difference between MTF live you can very well guess from this curve. If you analyze the population where you collect the data, the failure data of that, and you plot this data, the cumulative number folio versus time, you will find that this kind of curve you will obtain. That initial very early failure, then there is a stable period, and there is a rise of this number of failures. And if you model this in terms of failure rate, you will get a very common and very famous curve, which is known as Barton curve, which is the curve between failure rate versus time, which Dr. Rajesh has also shown you. So this curve shows a period of relatively very high failure, followed by a constant, and then there is a third period, what you call that, due to wear out, this failure rate starts again increasing. So useful life not begin until this. If you remove this part somehow through some testing, through some filtering process, then the useful life of the product begins like this, and this is followed by this. So MTBF, MTTF, what we talk about, it is this. It is the inverse of failure rate during this period. Here, if you are removing this and that, while the product is following all the phases. So the MTBF will give you an indication. You will consider that this is becoming the life without considering this period and this period. So this is defined as the reciprocal of the failure rate during the flat portion of the failure rate curve. So MTBF or MTTF are defined in terms of this portion of the curve where the useful life we consider only the useful life. The unit of failure rate is failure per hour. The unit of MTF, then it becomes hours per failure. Now note that it says nothing about how up to what point this infant the first phase will last. How high the failure rate during this period. When this failure rate or the wear out zone will begin. So MTF has no correlation with the onset of the variable. So it is not at all related with any of the portion, first portion and the third portion, but only you can relate it with the middle portion. So, and if you compute the reliability at the MTBF, it turns out to be 36.7% only or 36.8% only. So once you are specifying this requirement, are you thinking in this? Possibly not. Nobody wants that reliability after 10,000 is going to be 37% or so. It must be very high. So let us take another example that how MTBF will mislead you. So suppose there are 8 units are to be tested and the supplier has given the following data. If you compute the MTTF of that using Weibull analysis, so you will find both the supplier's product are providing you 10,000 miles MTTF. So which one you have to select? Are you going to select anyone? So based on this reliability metrics, the two suppliers' reliability can be considered to be equal. Now, let us see that how the reliability varies with respect to time. So, in the first case, say, so at 10,000 miles, you will see the reliability is vastly varies from supplier 1 to 2. Supplier 1 reliability is coming out to be 36.79, where the supplier 2's reliability is coming out to be 59.2. So this is the supplier 2, which has better reliability than supplier 1. So if you say that 50% chance of success or 50% with 50% confidence, what is the reliability? Here you can say the life of the product is. So you'll find the supplier 1's life with 50% confidence is 6930, and supplier 2's life is 10,066 miles. So in other words, supply 2 is closely matching the requirement, not the first one. So simply taking the MTTF as a reliability metric will give you a wrong notion. So the use of MTM can easily mislead a design team or contractor into the producing low reliability designs, as you've seen in the earlier slide. Likewise, possibly you can save some money on your test to prove that yes, MTM goals are released, are, are proven. So, in short, attempting to use a single number to describe an entire lifetime distribution can be misleading and may lead to poor business decisions. Let us take another example extending the previous example, the beaten life, where beaten life could be either the design life, warranty period, or whatever operation uses life is equal to 10,000 miles or 90%. In other words, the we expect a 10% failure over 10,000 miles. So it is a better matrix as it does not make the exponentiality assumption and it states clearly the percentile of failures by a certain time value. But certainly it lacks one component of reliability specification, that is a statistical confidence attached to. If you are estimating the reliability of that particular product, then how confident you are that the reliability is matching with this. So we can change to attaching a confidence 90% reliability at 10,000 miles with 50% confidence. So if you're plotting this, if you're saying that 50% confidence, then it is as good as not to quote it, because whatever analysis is done, reliability data analysis, they are done at the 50% confidence level. So just one example, see this. So design A, the failure times are there are 20 units which are tested and all have failed at different times. Likewise, the design B gives 4 units tested to failure. Now, if you see the plots, the reliability plots, unreliability versus time plots. So if you see that the probability of failure here 5%, right? It is well below. So 90% reliability will find that both meet the reliability requirement at 10,000 miles, because this is 90% reliability, the probability for failure should be 10%. So well below this, both are meeting the reliability, and design B has around 0.96 and design A has 0.95 at 50% confidence level. So both are meeting the design, reliability. So anyone can be selected. Now, if you look at 90% reliability, we see that, as I said, the 50% confidence level as good as not to specify that. But if we specify the reliability requirement as 90% reliability for 10,000 miles with 90% confidence, it means we want a minimum reliability as 0.9 with 90% confidence. Now, the statement, same as previous example, you see that, except that more confidence is put in. Let us see the previous example where we have the 20 units to test and design B has 4 units to test. Both are giving the same, almost close to same reliability. But Given this requirement, you see what will happen. Now, the lower confidence interval has been drawn. Red line and this line on the previous graph. If you see that at 10,000 miles, the 90% lower bound of reliability for design B is 79. This is the confidence bound because it is just a small unit, so uncertainty is very high, and hence they have the confidence bounds wider from the mean. And the design A has 90.41% reliability at the lowest level with 90% confident. So design A meets the requirement, which is much better than the design A. So up to previous example, we can go up to that. That will suffice the requirement. However, if you want to extend it, then one can specify 90% reliability for 10,000 miles with 90% confidence for 98th percentile of customer. Now, if your product, if you see that your product is going to be used in a variety of stress environment, say for India, the environment changes from cold to very hot. If you want the same product to be used, then that has to be tested at various stress level to satisfy the customer base which are residing at these varied environment. So then you will have to test your product. The testing cost is going to be very high because you are going to use your test your product at a variety of environment and stresses. Then only you can say that. Yes. So this is just explanation to that. That what is the meaning of 98th percentile customer? It means variety of stress level you have to test it because you have to satisfy the customers living at various geographical region, or you can say varied environment, and your product has to be used by those customers. So with this, so there are another area, the accelerated life testing, fault test, through which you can simulate these stresses and find out the failure modes or to quantify the reliability of your product. So coming to, possibly I am just in time possibly, but overshoot it under 5 minutes or so. So in conclusion, I just wanted to say that I wanted to convey this. One question is the system effective. Uh, the earliest definition of system effectiveness contains the ranks what we are talking about, and there are certain questions like how to specify the reliability for your product. This question, how you can address what should be the proper metric, not this MTBF, MTTF is not the correct metric for specified reliability. Or if you want to set out some target reliability for your system, you can go for three methods which has been discussed or briefly discussed in this webinar. With this, I conclude my lecture. Thank you very much for listening me. I had to, because of the time constraint, I had to skip many more things. Thank you very much.
Thank you very much, sir. It is always a pleasure to listen to you, and today you have actually told us about in depth about how to